Hello. In this video, we are going to discuss the hydrohalogenation of alkenes when there are no peroxides present. In hydrohalogenation, an alkene is going to react with a strong hydrogen halide with the general structure HX, where X will be chlorine, bromine, or iodine. Recall that hydrochloric, hydrobromic, and hydriodic acid are strong acids. Alkenes are a class of organic compound that feature a carbon-carbon double bond. And we can draw a generic alkene this way, where the groups R1, R2, R3, and R4 can be all the same, they can be different, they can be hydrogen atoms, they can be alkyl groups, they could even be halogens. The important thing for an alkene is that we have this carbon-carbon double bond. One important structural feature of an alkene, because of this carbon-carbon double bond, is the fact that the carbon-carbon double bond is stiff. It is fixed in place in 3 dimensions. Recall that carbon-carbon single bonds have very nearly free rotation around the bond. There's a slight barrier, but it's pretty small at room temperature. But the barrier for rotation around a carbon-carbon double bond is very high, so that at room temperature, this particular unit is going to be fixed in space. As a result, this particular unit here, for the first atom of R1, first atom of R2, for R3 and R4 groups, and the 2 carbons of the carbon-carbon double bond will all be in a plane. And this planarity of the alkene leads to some important chemical results. Let's look at the simplest and most important of the alkenes, ethylene, which has the IUPAC name of ethene. If we look at it edge on, we'll notice we can see the planarity of the carbon-carbon double bond and the attached hydrogen atoms. We've drawn the figures to show that while the 2 carbon atoms are in exactly the same plane as the whiteboard, the hydrogen atoms are pointing towards us, so they're closer to us than the whiteboard. There are also hydrogen atoms directly behind this hydrogen and that hydrogen, which we're leaving out here because they're silhouetted. The molecule is perfectly planar. Now, how the molecule forms the carbon-carbon double bond, the 2 bonds of the double bond are actually distinct, even though they're combining the same 2 atoms. The first of the bonds, the way we generally make a carbon-carbon single bond, is an overlap of a 2s atomic orbital on each of the 2 carbon atoms. And this makes our typical strong sigma bond. And then I've just erased the sigma bonds, the 2s orbitals on carbon that make the first of the double bonds, for clarity, to show you the important second part of the double bond. So for this bond, we actually have 2 p orbitals on each of the carbon atoms that are parallel to each other. And we draw the opposite shading to show the fact that p orbitals have a phase. They have a positive phase and a negative phase. And in the particular bond that we have for the carbon-carbon double bond, the second of the 2 bonds, they overlap in such a way that the lobes, so this is the top lobe, this is the bottom lobe, so the appropriate lobes on each of the 2 orbitals have exactly the same phase. So notice we have a positive phase with a positive phase and a negative phase with a negative phase. That tells us that we have a bonding orbital. So we have a so-called pi bonding orbital. So what I'd like to kind of show now is the result of this, by this overlap, is that we end up getting a buildup of electron density above the plane of the molecule and below the plane of the molecule, but not in the plane of the molecule from the pi orbital. So in the plane we have the sigma bonds, so there's electrons there. But the ones we're interested in here, the pi electrons in the pi bond, have their presence above the plane and below the plane. So it makes these regions electron rich, and these are the regions that electrophiles, such as our hydrogen halides, will want to react with. So up here and up here we have a buildup of negative charge, which I'll just kind of demonstrate by putting negative signs to remind us that those are the areas. So both above and below have equal amounts and the same amount of electron charge, whereas in the plane we have an absence of electron charge because in the p orbitals, remember that p orbitals have a node at the nucleus. So the p electrons cannot be at the nucleus, so they will not be in the plane of the molecule. To be clear, we're showing that there's a buildup of negative charge above and below the plane, but I don't mean to suggest that the overall molecule has a negative charge. The molecule, by definition of a compound, is neutral. Now, when it reacts with the hydrogen halide, we know that in an aqueous solution, hydrogen halides, HCl, HBr, and HI are all strong acids because they break up completely. Now, in this type of reaction, isn't necessarily so because we may not do it in an aqueous solution. But we have formation of H plus and the halide ion X minus. And our actual electrophile in this type of a reaction is going to be the H plus, the proton. So the proton is attracted to the buildup of negative charge either above or below the plane. It'll attack either side equally. And we notice something here. So here we have a species that donates a proton. Since it donates a proton, it is by definition a Bronsted-Lowry acid. But look from the point of view of the ethylene. Ethylene is accepting a proton. So therefore, by the Bronsted-Lowry definition, it is a base. But it's a kind of peculiar type of base because it's donating electrons that are in a pi orbital, whereas when we're used to things like ammonia, the nitrogen that makes ammonia basic has a lone pair in a sigma orbital, not in a pi orbital. So the kind of driving force of the first step of the reaction of hydrohalogenation is dissociation of the hydrogen halide, so the breaking of the HX bond, and then the transfer of the proton to the alkene. And in the process, we make a carbocation. And the kind of driving force of the reaction determines how fast the reaction takes place, and the types of products that we get is how stable the particular carbocation is that is formed. So we can use all the things that we know about carbocations and apply them to the hydrohalogenation of alkenes. So let's look at the hydrochlorination of ethylene. So recall that ethylene has this structure, and it has a carbon-carbon double bond, therefore it is an alkene. And let's suppose that it's going to react with hydrochloric acid. So the hydrogen-chlorine bond breaks, and chlorine takes the electrons with it to form chloride, leaving H+, and the center of negative charge on the alkene is the carbon-carbon double bond. So the way we show that with arrow pushing is to have an arrow going from the carbon-carbon double bond to the hydrogen atom. And as a result, we get the carbon-carbon double bond is transformed into a carbon-carbon single bond. And we are left with a carbocation plus chloride ion. And then in the final step, the chloride ion combines with the carbocation, and we have our product, ethyl chloride or chloroethane. Please see the following figures to see computed structures for the reaction of ethylene with hydrogen chloride and then with hydrogen bromide in the gas phase, and the resulting products of either ethyl chloride or ethyl bromide. The next most complex alkene has the following structure. And this goes by the common name of propylene or propene in the IUPAC. So now let's see the reaction with hydrogen chloride. And so long as there's no peroxides present, HBr and HI will react in exactly analogous fashion. So as recall, we have breaking of the hydrogen-chlorine bond, and chlorine takes electrons. We have electrons in the carbon-carbon double bond move to the hydrogen ion, the proton, and we form a carbocation. But now an interesting question arises because the hydrogen can become attached to either the first carbon or to the second carbon. So remember that our driving principle will be the formation of the most stable carbocation. If we have the hydrogen attached to the second carbon, the positive charge will be on the first carbon, and we would have a primary carbocation. So let's just show you the first possibility, what that would look like. So this is if the hydrogen goes to the second carbon. And notice we only have two hydrogens on the first carbon, so the positive charge would be on the first carbon. It may seem tricky, but whichever carbon gets the H plus doesn't end up with the positive charge. It's the other carbon of the carbon-carbon double bond pair that ends up with the positive charge. So if we were to add to the second carbon, we would end up with this particular carbocation, which we recognize as a primary carbocation. So let's assume that doesn't happen. So let's assume now that the hydrogen atom is going to combine and add to the first carbon. What we get in that case? So remember, the positive charge goes on the carbon that didn't get the hydrogen. So now we end up with a secondary carbocation. Recall that secondary carbocations are more stable than primary carbocations. So this is the product that would form faster than the primary carbocation. Once this forms, we have the simple recombination of the negative and positive ions, and as a result we end up with 2-chloropropane as our product. If we were to react with HBr, it will be 2-bromopropane. If we react it with hydrogen iodide, we end up with 2-iodopropane. So this idea that the hydrogen atom will go so as to form the most stable carbocation we call Markovnikov's rule. Another way to, instead of working out the stability of the carbocations, even though that's the principle that goes on here, we can simply look at how many hydrogen atoms are attached to each of the carbons. So this carbon here has one hydrogen, this carbon has two. In Markovnikov's rule, the proton, the H+, goes where there's already the most hydrogens. So by using that version of the rule, we can see that this hydrogen wants to go to the first carbon because it already has two hydrogens, more of its friends there, instead of just one hydrogen there. Please see the following computed structures for the reaction of propene with HCl and HBr. For the remainder of this video, we are going to look at the hydrohalogenation of alkenes with 4 carbon atoms. And we'll see that some interesting results ensue when we do that. So one of the alkenes with 4 carbons has this particular structure. And so we have 1, 2, 3, 4 carbons. So we know that the root that goes with 4 carbons is but, B-U-T. And we know that it's an alkene. So we know this must be some version of a butene. We always number the carbon-carbon double bond to make the numbers as small as possible. So we could name it from this end, 1, 2, 3. That would make it a 3-butene. But if we label from this end, 1, 2, 3, 4, then this is 1-butene. So we always want to use the smallest possible number. So this is 1-butene. So now let's react this with HCl. Remember that this bond's going to break. Chlorine's going to take the electrons with it, leaving hydrogen as H+. So now we have to figure out where the hydrogen is going to go when we have the attack of the carbon-carbon double bond on hydrogen. So when we draw the arrow pushing, we don't need to show that yet, but we show this is an electron-rich region going to an electron-deficient region. But when we want to look at what the product that we get is, we need to determine whether the hydrogen goes to carbon number 1 or carbon number 2. And we notice that carbon number 1 has 2 hydrogens, whereas carbon number 2 only has 1. So one way of thinking about Markovnikov's rule is the rich get richer. Since this carbon already has 2 hydrogen, it's going to get a 3rd hydrogen. Also, we see that by adding a hydrogen here, we make a secondary carbocation, whereas if we put the hydrogen onto this, added it to this carbon, carbon number 2, we would end up getting a primary carbocation, and secondary carbocations are more stable than primary carbocations. So our intermediate as formed here has the following structure. So once we add the hydrogen here, the positive charge, because it's short a pair of electrons, is on carbon number 2. And then we still have the chloride ion available, and chloride is going to go to the electron deficient carbon number 2, and we end up getting 2-chlorobutane. If we react with HBr, in the absence of peroxides, we're going to get 2-bromobutane. The reason for emphasizing the no peroxides is that HBr can also react by a different mechanism in the presence of peroxides, which we're not going to discuss here. But that's kind of an important point with HBr, which is different than HCl and HI, is that it has this possibility of reacting by a different mechanism, which would also give us different products. So that's the reason for me reminding you that the reaction with HBr that we're looking at here is in the absence of peroxides. Last but not least, if we react with HI, we would end up getting 2-iodobutane as the product. Please see the following computed structures in the figures to see for the reaction of 1-butene with HCl and HBr. We didn't show the reaction with HI just for the sake of brevity. We can draw a second 4-carbon alkene, which would have this structure. Now, the carbon-carbon double bond is between the between the second and third carbons, so we would refer to this particular compound as 2-butene. The number in front refers to where the carbon-carbon double bond is located. So, to vary this up a little bit, let's react this with HBr. Hydrobromic acid. The first step is the heterolytic cleavage of this bond. The electrons go with bromine to form bromide. We have the electron-rich region here, transfers electrons to the hydrogen, and then we have an interesting question. Will the hydrogen add to carbon number 2 or to carbon number 3? And because of the symmetrical nature of this molecule, as we would have in ethylene, for example, it doesn't make a difference. If we add the hydrogen here, the positive charge would be there, and we'd have a secondary carbocation. If we add it to this carbon, the positive charge would be here, and we'd have an equivalent secondary carbocation. So let's show what that looks like. Let me actually show the hydrogen in brown so you can see where it went to. And we notice, since this carbon has 4 bonds to it, it's going to be neutral. This carbon only has 3 bonds, so it's missing in a lone pair. So the positive charge must be there. So here we have a secondary carbocation. And what happens for the rest of the reaction? We have bromide here. Remember, it took the electrons with it. So now we have bromide bringing its electrons to the positively charged carbocation. And notice what we get. We end up getting 2-bromobutane. If we react it with HCl, we would get 2-chlorobutane. If we reacted 2-butene with HI, we will get 2-iodobutane. So notice that whether we started with 1-butene or 2-butene, even though we move through different intermediates, we end up getting exactly the same products. So please see the following figures to show computed structures of 2-butene and the carbocation intermediates and the follow-up products for a reaction with either HCl or HBr in the absence of peroxides. Now we will look at our third and final 4-carbon alkene, which will have this structure. And this is a compound we call 2-methylpropene. But it also goes by the common name of isobutylene. In fact, it was this specific compound that Markovnikov did his first researches into the hydrohalogenation of alkenes with. So let's look in this case, just to show all the possibilities, let's react with hydroiodic acid, with HI. So we know the mechanism. The first step is the breaking of the hydrogen halide bond heterolytically so that the electrons go with the halide. And then we have the electron-rich carbon-carbon double bond, transfers its electrons to the proton, which is positively charged. And we get our intermediate. Let's draw what the intermediate looks like. So here's the interesting thing to think about before you even draw that, is that where is the hydrogen going to go in the carbon-carbon double bond here? Well, we see that carbon number 1 has 2 hydrogens attached to it. This carbon has 0 hydrogens. So if we apply our rule that the rich get richer, this hydrogen is going to go to the first carbon because it already has 2 hydrogen atoms as opposed to this carbon, which has 0. We'll also see that if this hydrogen would go to this particular carbon, we would the positive charge would be on the other carbon. We would have a primary carbocation. But let's see if the hydrogen adds to carbon number 1, what type of carbocation we get. Remember that as we add H+, the carbon-carbon double bond gets transformed into a single bond, and the positive charge that comes from H+ goes to the carbon that didn't get the hydrogen. That's kind of may seem backwards, but that's how that goes. So here's the hydrogen atom adding to the first carbon, which already has 2, and then the positive charge will be on the other carbon. Let's see what that gives us. Well, we see here this gives us a tertiary carbocation. And recall that tertiary carbocations are the most stable of all. They're more stable than secondaries, which are more stable than primaries, which are more stable than methyl carbocations. So here we have this particular structure. When iodine adds, we end up with a tertiary butyl iodide, or we could call it 2-methyl-2-iodopropane. The more official name, more commonly would be called tertiary butyl iodide. If we react with HCl, we would have tertiary butyl chloride. If we react it with HBr, we would have tertiary butyl bromide. So we see that depending upon which of the 4-carbon alkenes we start off with, we may or may not get different products based upon this idea of Markovnikov's rule. Please see the following figures to see the structures of the reactants and products and intermediates in the reaction of 2-methylpropene with either hydrogen chloride or HBr in the absence of peroxides. As always, I thank you very much for your kind attention. Have a good one.